Welcome to General Chemistry Mini Lecture Series, Lecture 38, Effective Nuclear Charge and Magnetic Properties. In atoms, the core electrons shield the outer electrons from the full effect of the nuclear charge, which is positive. The net nuclear charge actually felt by outer shell electrons is called the effective nuclear charge, ZF. And ZF is normally lower than the actual nuclear charge, which equals to the atomic number. The equation for calculating the effective nuclear charge is atomic number, that is also the actual nuclear charge, subtracted by S. S here means shielding. The S value is actually the number of core electrons, because core electrons shield the outer electrons. Now, the trend for effective nuclear charge is increasing from left to right across a period. An increasing effective nuclear charge means that there is a stronger attraction between the nucleus and the valence electrons. Now let's take a look at penetration and shielding. We'll use lithium as one example. Atomic number for lithium is 3, so therefore there should be 3 protons and the nuclear charge should be 3 positive. In a lithium atom, there should be also 3 electrons. Those 2 are the core electrons, and this one is actually the valence shell or outer shell electron. The 2 core electrons, they will be traveling all the time in this region, and then this valence electron will be traveling in this region. Between the valence electron and core electrons, there is a repulsion force, because electrons are negatively charged, they repel each other. However, this negatively charged valence electron is actually attracted by the positively charged nucleus. Therefore, this is called attraction. However, this attraction is weakened by the shielding of the core electrons. Let's take a look at this illustration. The same lithium atom, actual nuclear charge is 3 positive. And now if we concentrate on the core electrons, this core electron should experience the full 3 positive charge. The effective nuclear charge should be 3 minus 0. 0 means there's no shielding. There are no inner electrons anymore to shield this electron from the positively charged nucleus. So this phenomenon is called penetration. Now look at the opposite. The same lithium atom, and those are the 2 core electrons. Now let's focus on this valence electron. Because those 2 core electrons, they repel this valence electron, then this valence electron experiences much less nuclear charge. So we can find the effective nuclear charge for this electron by using the same equation. ZF equals Z. Z is the actual nuclear charge, subtracted by S. And then Z is 3, S is 2. So therefore, this valence electron only experiences a net charge of 1 plus. not 3 plus. Why? Because of shielding. Those two core electrons, they shielded this outer shell electron from positively charged nucleus. That's the penetration and shielding. If transition metals have unpaired electrons, they are attracted to a magnetic field, and this phenomenon is called paramagnetism. On the other hand, for transition metals and ions with unpaired electrons, they exhibit no magnetic field. So we call this diamagnetism. Let's work on example 1 in lecture 38. We need to write the condensed electron configuration first, and then determine the magnetic property, either paramagnetic or diamagnetic. For iron, iron 2 plus, silver, and silver plus. For iron atom, there should be 26 electrons, and its previous noble gas is argon. Therefore, the electron configuration for iron atom is argon, then followed by 4s2, 3d6. The total number of electrons should equal 26. It looks clearer when we use orbital diagrams. Obviously, there are unpaired electrons. So in this case, those orbital diagrams are much more helpful, because without those, if you look at 4s2, 3d6, they are all even numbers, then there are no unpaired electrons. That's wrong, remember? Because of Hand's rule, actually, we do have unpaired electrons. So therefore, iron atom should be paramagnetic. Iron 2 plus, losing the 2 4s electrons, there are still unpaired electrons. So therefore, it is still paramagnetic. How about silver atom? The atomic number is 47. Therefore, there should be 47 electrons. And the previous noble gas is krypton, 36 electrons. Here is silver atom's electron configuration, krypton, then followed by valence electrons, 5s1, 4d10. Let's look at the orbital diagram. There is one unpaired electron. Therefore, it should be paramagnetic. How about silver 1 ion? The 5s1 electron is lost. That electron is lost. And now everything is paired. So therefore, diamagnetic. That's all for lecture 38. If this video is helpful, please subscribe to this channel. And you are also welcome to recommend this channel to your friends who are also studying chemistry. I will see you guys in lecture 39, periodic properties.